So here's a cross plot, and you'll find this cross plot conventionally in the Schlumberger charts. Schlumberger, Baker Atlas, Halliburton, all the rest of them, they're on this game. And we see a cross plot of potassium and thorium for that section. And here's the Cedar Hill sandstone, feldspathic sandstones, but they're plotting down here separately from these shales up here, which have about the same amount of potassium. They just have more thorium. So we can look at the cross plots if it helps us, and certainly for the digital logs, we're in great shape to do this kind of cross plot. So there was the issue, sure. The kick's there, but look, lots of thorium here, and it's only down there that the thorium slumps. Potassium's holding it, so that's why that contact's right there. Otherwise, as we look at the sequence, though, we can see then that the difference between the SGR and the CGR, remember, is the amount of uranium, and there's really not much at all, until we get to this point here, and that's at the top of the Dakota, where now we are getting the transgression then. This is the Upper Cretaceous going to the Graneros, which is a black shale, got a lot of uranium in it. The sea is getting deeper, if you like. Greenhorn limestone, this is where your fence post limestones are if you go out west. And then this is the marine regression as we go up here. So actually we're seeing a massive signal of the seas coming in and the seas going out. Otherwise, we can look then at the thorium-uranium ratio, and this gives us an idea then of relative uranium richness. So down here, anything that's higher than 7 is where you've got very little uranium in that aspect there, anything higher than 7. So you get depleted uranium, and this is where we're getting enriched uranium, where we get the lower numbers, because a lot of, so these are your black shales then. You're getting a lot of uranium as related to thorium. And here's a slide in aspect. I've always been interested, and maybe some other people are too, in the good old beach island zone. So as people then do shallow gas exploration up there in northwest Kansas, up in Colorado or Nebraska, very commonly, if you look at the gamma ray curve, here we're looking at the Niobrara Chalk, and here's the beach island zone, we say it all looks quite radioactive. We say, boy, that must be really shaly kind of stuff. Now look at the scale the logging engineer chose, 0 to 400. Now why did it span that scale? Because if the logging engineer had chosen 0 to 150, you'd have this very annoying property of going backwards and forwards on one scale to the other. The logging engineer said, no, I'm going to try and make life easier for you, and I'm going to plot this curve here. So these gamma ray values then are way up 150 through that whole sequence. So what we're looking at then is we've got the Niobrara Chalk here, and here's our potential gas zone right there. Then we've got the Sharon Spring Shale up here. Now watch what happens though if we look at the CGR. All of this is uranium. So it all dropped out. I can't say it's clean because we still have this amount here. It's certainly got some clay material in it, but a lot of this is uranium. So what's going on here? Well, you got gas. Where's that gas coming from? It's biogenic gas. There's a lot of kerogen down here, and that kerogen then is associated, in this case, quite commonly happens with a lot of uranium. And anybody who's looked at gas shales, for example, think, this rings a bell. You got gas shale, you got gas, it's coming from kerogen. Very often the kerogen is strongly linked with the uranium content. So for whatever reason, bless their hearts, they ran a spectral gamma ray log on this one. So we could say, here's the smoking gun. This stuff here is mostly uranium associated then with the kerogen content. And then we go above. This is our Sharon Springs. And so, yeah, it's kicking up. It says, oh yeah, that's a shale starting to develop, no question on that. But again, it's a black shale and it's got a lot of kerogen material. Notice over here though, when they put out the thorium, the uranium, and the potassium curves, that on the one hand, let's look at the thorium. Reading very low values here, a little bit, clay material in the nitrogen, and then whoa, it kicks out very strongly. That's the Sharon Springs shale. No problem. Uranium's really interesting. Look at this, bumping around all over the place. Now this is something that a geologist would love, so engineers could go to sleep on this, but it's kind of interesting to me. Look at that nice uranium spike right there on the top here. So it's quite common, unconformities and so on, you can see a uranium spike develop. And that would match what happens, say, in Australia today. You look at calcretes out there where they do uranium mining, extensive leaching, and so on. So I'm starting to get into the geology aspects, but at the same time, a lot of these things feed back into telling us what's going on then as we interpret the curves more from an engineering aspect, saying, I really don't care, I just want to know what's going on the beach island zone and whether I'm likely to produce gas and what's happening there. For geologists, where it turns out interesting, because as you go up into above this section here, you'll actually see some distinctive thorium spikes, and those are picking up volcanic ash deposits up there. So, but anyhow, that's just a side piece of geology. Now, the other aspects then are looking at the other logs, and that is, again, we'll focus to start on the neutron and the density. So neutron porosity, bulk density, again, these are nuclear logs. But in this case, rather than measuring natural radioactivity, you have sources, a neutron source, which is pretty nasty, which is loaded then on the neutron tool, and also the density. So on the density tool, it'll be a source of high energy gamma rays, which is being loaded on the tool. So now we're seeing what happens when we bombard the formation with these radioactive particles. And that'll be sensitive to, on the one hand, porosity, which is really why we run them, but also sensitive to the kind of rock we're looking at. Usually today, what you'll see is the neutron, the density overlaid, and this will come directly off the logging truck. One reason is that they're run together, and the second aspect is that it helps you if you've got two porosity logs, because if you are going to get a porosity, you have to use a reference lithology. And that's always been the nuisance, that, for example, if you look up here, you can see they are scaled with respect to limestone. On the other hand, we could have it scaled with respect to sandstone or dolomite. And so there would be an issue then, if you're going to use simply a density curve or a neutron curve by itself, you have to say, what is the geology that I'm looking at? Because if it turns out that you look above and you see the neutron scale to limestone, you're going through a sandstone, that's not right. You have to use a sandstone scale. Furthermore, it gets even worse if you get a mixture of them. If you get sandy limestones, you say, now what do I do? It's a problem. So that's always the issue. And it's an issue you get kind of reminded of all the time. At least I do. I keep reminding myself. Once, years ago, I was out on a hole in Russell County, and I couldn't figure it out why the sonic log porosity looked so weird. It didn't make sense to me at all, because after all, we were going through Lansing County's Kansas City limestones. And I think maybe it was Bill Guy who said, I think if you go and talk to the logging engineer, you'll find out why. So it was a Schlumberger thing. I talked to the logging engineer. Well, he was from Venezuela, and he was running everything on a sandstone scale. And I said, but you're not in Venezuela anymore. You are in Kansas. But nevertheless, it does mean if you have a single porosity log, you better check out what they're scaling to and see that it matches up with your lithology. Now, the nice thing about it, though, is if you have both the neutron and the density run together, which is the common practice with just about any logging company now, you can actually extract what you want to know. That is the true volumetric porosity regardless of the kind of lithology. So up here we see neutron density, limestone equivalent porosity. They're both scaled that way. So as usual, we've got the porosity increasing in this direction here. That, by the way, is the convention that's always been used. One of the reasons, and I think Richard was picking up in terms of Jim at Amoco, was that by looking at the separation, you can look for prospective zones.